So why don't we start right away with just doing an area problem, okay? That we learned yesterday, really. We want to remind ourselves of the sequences that we need, right? We need the sum of a constant from I equals 1 to n is n times c. So if like I add 5 up n times, right, it'd be 5 times n, right? Or n times 5. If I just am adding up my indices, right? So 1 plus 2 plus 3, right? I get n times n plus 1 all over 2. Again, search for proofs by induction if you want to see it proved. From I equals 1 to n of the indices squared. Remember, the indices is just me counting the first rectangle, the first number, the second number, the third number, right? So this is 1 squared plus 2 squared plus 3 squared plus dot, 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 all the way up to n squared. And I get n times n plus 1 times a 2n plus 1 all over 6. These things have been proved probably 800 BC. These were proved. The sum of I equals 1 to n of I cubed, the indices cubed. So 1 cubed plus 2 cubed plus 3 cubed plus dot, dot, dot is n squared times n plus 1 squared all over 4. There are more, but we don't go higher than this for our purposes of showing that that the integral is a sum, okay? And if you notice what I'm building here, does anybody see what I'm building? What am I building with these? What kind of mathematical function am I building with these? Yeah, polynomials, exactly. So when I'm doing integrals with this, these are called Riemann sums, by the way. I think I know how to spell it. I don't. I think it's 2 n's or something. I don't remember. Don't trust me on my spelling. But if you're reading the section 5.1, 5.2, 5.3, you'll read about it. So we're just, when we're doing these Riemann sums, we're going to use polynomials. Okay. So here we go. Here's our first problem today. We want to find the integral, let's say from 1 to 4 of, let's say, x minus x squared. And we're going to do this two ways on the test. We're going to do it first with the definite integral. So I actually want you to find the area here, right? And then with the Riemann sums, with these sequences. So we know that this is going to equal the limit as n goes to infinity of the sum of the first to the nth rectangle with a height of f of x sub I and a base of delta x, right? And automatic, we know delta x is b minus a over n, and x sub I is a plus delta x times I. So these things have kind of been figured out for us, but you know, it really came down to that picture. Right? It really comes down to that picture of me drawing those rectangles. So what is this? This is 1, right? And so, yeah. And so I was building those right-hand rectangles, right? So we're talking about area under the curve. That means if the curve's above the axis, we have a positive area. If the curve is under the axis, we're going to have a negative area. Okay? Right, so this is x sub 1, this is x sub 2, this is x sub 3. Of course, the width is delta x, right? And the height is f of x sub I, right? The height of that one rectangle, right? And we're adding up all of those areas. Yeah, we're comfortable? We know what's going on? So let's do the left-hand side first, because that's easy, right? Let's do that left-hand side first. This is my area problem. And there's a nice website here called GeoGebra, GeoGebra.org. GeoGebra, it's like algebra and geometry scrunched together somehow. So GeoGebra. And in my search box, I'm going to do Riemann sums. Yeah, I did have it spelled right. No, I had the I first. So there's lots to look at. I think this one is pretty nice. I want to pick one that I can change the function, right? And set my limits and say how many rectangles I want. So I just picked that very first one here. Come on. Here we go. So what did I have? X minus x squared, right? And I wanted to go from 1 to 4. So this is a real nice way to get a visual of what's going on. I don't know if they're using right-hand rectangles or not. They're using left-hand rectangles. You can see it. But the idea is if I just increase my number of rectangles, right? So by the way, the first rectangle, there's 5 rectangles there. It's hard to see. But they're using left-hand rectangles, okay? So that means the height is coming from the left-hand point. Remember, I'm starting at 1. Can you see my mouse there up on the screen? Can you see the hand pointing? So if the height for that first rectangle is from this point, that's 0, right? So the height is 0. The height here, right? So this is a left-hand rectangle, right? And again, try and make sure you read through the book and do left-hand rectangles and midpoint rectangles before you take Calc 2, okay? Yes? Just acknowledge, please. Yes? Good, thank you. So, left-hand side, which is the easiest, that's how we like to start. We like to check it with Desmos. So I'm doing the integral from 1 to 4 of x minus x squared, right? And so what's the, what do I get when I do the antiderivative here? What's the antiderivative of x to the 1? Yeah, add 1, right, to the power and divide by 2, right? And then what's the antiderivative of x squared? Yeah, add 1 and then divide by 3. And then evaluate at 4, evaluate at 1, and subtract. So I get x squared over 2 minus x cubed over 3, evaluated at 4, and then at 1, and then subtracting. And again, I'm doing, this is called a definite integral. It's giving me the area underneath that curve, right? So let's see, what do I get here? I get 4 squared over 2 minus 4 cubed over 3 minus 1 squared over 2 minus 1 cubed over 3. Right? So I'm evaluating at 4, evaluating at 4, the whole thing, right? Subtract, evaluate the whole thing at 1. Yes, we okay here? 16 over 2 minus 64 over 3. Is that right? 4 cubed is 64? Yeah. Minus a 1/2 plus a 1/3. Oh, 63 over 3 is 21, right? So I need a 2 over 2 here. So I've got 15 over 2 minus 42 over 2. So what is that? Negative 27 over 2. Agreed? Yes, everybody okay? We want to check on Desmos because we're trying to check everything we do, right? We want to be correct. We want to know we're correct before we order that part to be printed for this engine I'm building, right? Or this machine I'm building as an engineer. I want to make sure it's correct before I go order it, right? So I'm doing the integral INT. We'll start my integral from 1 to 4 of x minus x squared with respect to x, dx, right? And there it is, negative 3.5. Is that what I got? Negative 13.5? Yeah. Right? Yeah, we comfortable? It's pretty cool. You'll see in Calc 2, you'll see what these integrals will give us, right? We already know what the derivative's giving us, telling us how things are changing, right? Telling us concavity, that type of thing. Good, now the right-hand side. I'm looking at what negative, help me, what did I say, 27 over 2? As the limit, as n goes to infinity, of the sum of the first rectangle to the nth rectangle of f of x sub I times delta x. Well, we need to know, right, we need to know a couple of things. We need to know delta x. So delta x is 4 minus 1 all over n, so that's 3 over n. Everyone okay there? We need to know x sub I. That's 1 plus 3 over n times I. Right? So think about where I'm starting this first rectangle, right? Where that first rectangle is starting. Obviously, it's starting at 1, right? You see the rectangles are starting at 1. So that's why we're doing a plus delta x times I. We want to find f of x sub I, and this is usually the trickiest part. So I need x minus x squared, right? And inside of that, I'm putting in my x sub I. So 1 plus 3i over n, 1 plus 3i over n. Right? Everybody with me? I want to simplify this and be careful with it, right? Just make sure you're taking your time. So I get 1 plus 3i over n minus, I'm going to FOIL this, right? 1 plus 6i over n plus 9i squared over n squared. So I'm just doing all that FOIL piece in my head. If you can't do it in your head, do it on paper, right? It's better to be thinking on paper than thinking in your head. So I get 1 minus 3i over n minus 1 minus 6i over n minus 9i squared over n squared. So some things cancel and some things can be combined. It looks like I get f of x sub I is minus 9i over n minus 9i squared over n squared. You're checking me, please. Hopefully, right, you'll catch a mistake, because it's horrible when you do this and it takes 2 pages and then you have a mistake somewhere, because we already know the answer. So we're hoping to get the same answer, right? Usually what's going to happen there is, you have your left side right. You're going to have to do your right side over, most likely. Again, yes, you can look for mistakes, but it's often easier just to start over and make sure you're not going too fast or not checking things, right? So our integral, right, from 1 to 4 of x minus x squared dx. Yeah, say again. Good question. Thank you. Thank you. So that's a negative 3i, right? Yeah, thank you. You saved me. Again, I'm looking at the limit as n goes to infinity, and I'm going to start to shortcut this because I'm getting a little bored, is the sum from I equal 1 to n of negative 3i over n minus 9i squared over n squared times delta x, which was 3 over n. Right? How we doing? We okay? We okay? Good. I'm pretty lazy, so I'm going to start to shortcut, and I invite you to do the same thing. I'm going to be saying that this is the limit of the sum. So I'm going to stop writing all those little indices, right? I'm going to stop writing where my limit's going to. I know it. I'll put it back later at the end. So what do I get here? I get negative 9i over n minus 27, over n squared minus 27 I squared over n cubed. Right? I'm just distributing that piece in, right? I'm going to distribute my sum, right, to 2 pieces. So I have the sum of minus 9i over n squared plus the sum of minus 27i squared over n cubed. Again, my sum is dependent upon I, so everything else can be considered a constant. Constants can move out of the sum. How? By factoring. Or they can move back into the sum by distributing, right? So there's really not too much to think about there, that I can now say that this is the limit of negative 9 over n squared times the sum of I minus 27 over n cubed times the sum of I squared. We okay here? Now these 2 pieces we have information about. We know what those sums are. So that's what we're putting in now. I'm doing, yeah. Were you at line 3?
No,
You're just processing? Yeah. I just had did I have coffee? Oh yeah, I just had a coffee and probably just going too fast. Good. So we know the sum of I, right? So this is negative 9 over n squared times n plus 1 all over 2. And we know the sum of I squared, that is n times n plus 1 times 2n plus 1 all over 6. And I want to simplify as much as I can. So it looks like I get negative 9 over 2, 9 over 2n, sorry, times n plus 1, right? Make sure you agree. One of the n's canceled there, right? I get minus 27 over 6n squared times, and I'm distributing here. So n plus 2n plus 3n, oh, sorry, 2n squared plus 1. So I canceled one n, make sure you see this. I canceled one n, and I distributed the other piece. Yeah, we okay there? I'm going to keep going. So minus 9n over 2n, minus 9 over 2n. I'm distributing, right? Minus 54 over 6n, 54n squared over 6n squared. Minus 81n over 6n squared. Minus 27 over 6n squared. Again, just distributing here. I see two pieces that are actually, what did I do? No, nothing. I see two pieces that are going to simplify a little bit, right? That I can actually combine. I'm going to put those first. So I've got a minus 9 over 2, minus 54 over 6. And then everything else I'm going to keep here. Minus 9 over 2n. Minus, don't tell me, 27 over 2, and then finally minus 27 over 6n squared. That one's, oh, I could cancel a 3 there. I don't have to do that. The key is that I'm seeing that I've got a leftover n in all of these. So what's going to happen when n goes to infinity? All of those pieces are going to go to what? 0. So my limit, right, as n goes to infinity becomes, oops, sorry, I already knew that. Just becomes minus 9 halves, minus 54 over 6, minus 0, minus 0, minus 0, right? When I take that limit, yes? Come on, get rid of this stuff. Get rid of this. I don't want this. Help me, 54 over 6. Yep. Yeah, go back up. Yeah, so line 5, 6, 7. Yeah. That's right, I got minus 9 halves. Yeah, so there I canceled my n squared. Right, that's an n squared, sorry. That's why it probably looked weird. Yeah, and then I left everything. I try to simplify, but I don't have to, because I see the power here of n is higher in the denominator higher in the denominator, higher in the denominator. So we know right from that limit at our chapter on limits at infinity that those pieces go to 0 when I take the limit. 54 divided by 3 is what? Thank you. All right. Here it is. Negative 27 over 2. The right answer. Right? So any polynomials up to degree 3, don't go past that. Okay? So you could create any type of problem you want yourself. Right? I typically keep it to quadratics. So up to I squared things. Right? So you can make up your own problems for this, which is pretty interesting. So believe it or not, we have done 5.1, 5.2, 5.3. And 5.4, I only talked about it theoretically. I'm talking about simply that, what do we say, fundamental theorem of calculus, taking a derivative or taking an antiderivative, those are inverse operations, right? So there's a nice way to see this. I don't know if I can do it on Desmos, but I want to show you at least on the calculator. So I put in my function that I'm integrating, which was x minus x squared. I make sure I get a picture on my graph of the function of the bounds of the integral I want. So from 1 to 4, I want to make sure I can see 1 to 4, right? And I go to second, calculate, hit number 7 for integrate, tell it my lower limit and hit enter, tell it my upper limit and hit enter, and then it shades the area onto the curve. And again, it's from curve to x-axis, right? So area underground is negative. Yes? So Desmos is enough. I don't know. Let me see if I can get something like that on Desmos. I don't think I can. I want to go back to home. Oops, sorry. I thought I could search. Let me do it this way. Desmos Riemann sums. Let's see if I can come up with, see if anybody's created something. Oh my, is it slow? Come on. No, this is just having you build it yourself. So, it's okay. Nice. So we're quizzing today on 4.1, 4.2 and 4.3 first derivative test. Any questions for me on that? Any questions in the homework 4 or anything? Yeah, which one? Yeah, which problem? I mean, I'll look at the functions and we'll pick one, okay? Oh my God, so slow. Uh, yeah, any of those functions up to 16 is fine. Pick one for me. Nah. Sure. ln of x over square root of x. So there's my function. I want to do a first derivative test here. Do you notice my domain here? What's the domain here? X has got to be greater than what? Greater than 0, right? Certainly when I go to graph it, I will see that as well. Oh my God, what is going on? Y equals ln of x all divided by squirt x. So I certainly can see my domain here, right? You should be really comfortable with domain, especially after a pre-calc class. So I already know my number line that I'm going to fill out later with my first derivative test is going to do something like 0 to infinity, right? Right, you with me? I need that number line on my desk from second grade to be the domain of the function, right? I need a derivative, right? So my upstairs function is what? ln of x. Derivative is 1 over x. Downstairs function is square root of x. Derivative is 1 over 2 square roots of x. And of course the downstairs squared is just x. I'm doing the quotient rule. Right, everybody okay here? So I need square root of x over x minus the ln of x over 2 square roots of x. I don't care too much about being perfect with my LCD because I always can simplify things. So I don't know if you could see what could be simplified here, but if you don't, that's fine. You just want to create your LCD. So I'm missing a 2 square root of x here, right? And on the other one, I'm just missing an x, right? Yes, you with me? Nice. So my derivative now looking a little bit better. Sorry, I don't want to cancel anything. Downstairs, I definitely have 2x square root of x And upstairs, it looks like I have 2x minus x ln of x. We agree with that? Of course, I can factor out an x upstairs, and I want to. Because I can see that that's going to cancel, right? So I have 2 minus ln of x over 2 square roots of x. How are we doing? Question? Yes? So let me give line here, right? 1, 2, 3, 4, 5. Between 3 and 4. Oh, thank you. God, Robert, what the hell is wrong with you? So now I can go 2 minus ln of x over 2 square roots of x times 1 over x, right? Thank you. Doesn't change my it doesn't change my criticals, but we gotta be more careful, right? We gotta be careful. We have to be precise. We want to be double checking ourselves. So on that one, before I go finish my first my test, I want to go check and see if I got my derivative right? And you all know how to do that on Desmos, yes? You all know how to do that on Desmos. Check your derivative. Yeah. So, I mean, it's kind of interesting for me to have done that, right? So what am I going to do? I'm going to double check my wrong derivative. So d dx, right, my operator for derivatives, there it is. And then I'm going to put in what I got wrong, right, which was what? 2 minus ln of x all over 2 square roots of x. And look, I see it's not correct, right? But if I throw that other x in front here, look, it matches up. So I mean, I make mistakes, but I want, you need to practice so you make mistakes, and then so you can fix them, right? You don't want to be making the mistakes the first time on the test. You want to do it at home, right, on the homework. Okay. I've got my derivative. I need criticals. Yes? So f prime of x equals 0 implies the numerator is 0. So 2 minus ln of x equals 0. That means what? Ln of x is equal to 2. That means x is equal to e squared. Right? Yeah. So from you're okay here, you're okay here. Am I right? Yeah. Then I raise both sides base e, right? And e and ln are inverse properties, inverse functions, so they cancel each other out. And just get the x here. I know f prime of x does not exist implies the downstairs equals 0. Of course, that just means x is 0. But that's already not in my domain, so I'm not too concerned about it. It's already on my first derivative test number line, right? But I don't have to check left of it. So all I care about is checking between 0 and e squared. Right? You with me? Now, I'm in trouble here a little bit if I just trust the graph, right? And in fact, let me see, what do I get at f of e squared? I get ln of e squared over square root of e squared. I get 2 over e, right? We did this the other day, I'm pretty sure. So I want to get rid of my derivative here. And I want to plot that 1 point, e squared, comma, 2 over e. It is awfully difficult to tell, maybe not really, that this is the high point. I can kind of reason out that I think the curve looks like it's going, closer to the x-axis after that point. So on this one, I'm kind of, instead of using the curve to verify my calculus, I'm really just using the calculus, right? So give me a nice number to the left to test in my derivative. It should be obvious to you what I would like to use left of e squared. What number? Yep, and what number to the right? E cubed, right? Something simple, right? I think I already see what's happening for my first derivative test. I think it's increasing, so first derivative is positive, and then decreasing, first derivative is negative. Right? But let's double check. Let's take our derivative, right? And double check e. Ln of e is 1. So I get 2 minus 1 over 2e to the 3 halves. So I definitely get a positive number. Right? To the derivative, exactly. When I'm doing my first derivative test, I'm testing my test values in f prime. When I'm going to find my local max, I'm going into f. Let's double check e cubed. So ln of e cubed is 3. What do you know? Say again? Correct. That's correct. They're inverse operations. Inverse functions. And that's negative. Just like I thought, right? I want to be careful of it if the graph could trick me. So I want to make sure I double check with calculus, right? What's my conclusion? Since f prime of x is positive on 0 to e squared, f is increasing on the same interval. And you don't have to number them, I'm just pointing out I want to find increasing interval, decreasing interval, and if I have local mins or maxes, right? Since f prime of x is negative on e squared to infinity, f is decreasing on that interval. Since f prime changes signs at x equal e squared from positive to negative, and f of e squared, which was 2 over e, exists, right? That point exists, it must be a local max. In this case, it's the absolute max, but we don't care. right? I'll ask you that question if I want to ask you that question. But when we're doing first derivative tests, we're just looking for locals. Local high points or local low points. Exactly, to get the point on the curve. Put the test values into the derivative or the second derivative. To find local mins or maxes or inflection points, you plug those criticals either from the first derivative or the second derivative back into the original function. How we doing? Okay? Yep. No rush. I'm Polish, not Russian. No, you can just tell me what you found out. Yeah. I try not to be, I want to be rigorous, but not picky. I used to be a really picky teacher when I taught guitar. It's a joke. Good. Any other questions you want me to talk about? Nice. Let's go back to integration methods. Yay. So, I mean, because I was a half hour late, I'm not really seeing a break in our future, but if you need to take a quick break, feel free. I am recording. We got up to level, I think we got up to level 6, substituting downstairs, right? So we kind of going to look at our whole list here first. So you don't have to write this again. You have it already, okay? So this is my integration checklist, or integral checklist. You know F prime, right? So that's the one where I see something I already know, and I can just write the antiderivative, right? That's level 1. And you'll notice things turn into level 1. Things turn into level 2. And so when I ask you this on a test, it's gonna start at level 9 and then move to level 4 and then move to level 1, right? So just be ready for that. Step 2 is a power rule, right? Level 2 is a power rule, like x squared, right? That becomes x cubed over 3 plus c, right? Add 1 to the new power, divide by the new power. Level 3, we had a couple of tricks, right, that we're going to see come into play more often, but you've definitely seen multiply by 1. You haven't seen add 0. Oh yeah, we did that. We did long division, right? So what did I say? Long division, divide and conquer, add 0, multiply by 1. We've seen that one for sure. Complete the square. You'll see that hopefully tomorrow. I don't think I'll get to it today. At least not without hurting you. So and maybe more. I'll keep adding to that. Level 4 was we started U subs, okay? And that's really what section 5.5 is called, U substitutions in integration, right? So this is our first U sub. We're going to set U to be a function and U prime to be the derivative dx, right? Right? So obviously the function is, and I could do either way. I could pick sine of x as my function or cos of x as my function because I have the derivative there, right? So the easier one in this case is to let u be sine x, and then du is cos x dx. So I get u du, right? Of course that's u squared over 2. So it's sine squared x over 2 plus c. Right? So see a whole function and its derivative, like ln of x and 1 over x, like arctan of x and 1 over 1 plus x squared, or et cetera, right? Level 5 is u becomes the inside, right? If we see a complicated inside, a clear inside, we're probably thinking that's the way to go. So, for example, right, just something as simple as this. There's clearly an inside, right? You agree? So we say here u is the inside. Of course, du is 2 dx. And that's where I'm doing my level 3 trick, multiply by 1. I'm multiplying by 1 by a 2, and I'm canceling with a 1/2. Right? So I get 1/2 of square root of u du. Right? Make sure you see that the 2 dx is du, right? Level 4, a whole function is our u. Level 5, the inside is u. Level 6, the downstairs is u. We just did that one yesterday at the end of class, so let me do a couple of those before I add the next method. Okay, so let me go to that particular chapter, section 5.5. And let's see if we can find one. Right? What do you think? You see one there that looks like it might fit the bill? Where I can take the whole downstairs as u? Well, 15 works. Let's do 15, okay? Can you even see can you even see this? So 15 works and 18 works. And again, you're going to let the checklist develop, right? I'm saying, hey, start. I'm giving them to you in order, just like I would give you notes, like when you first learn how to play a scale, do, re, mi, fa, sol, la, ti, do, right? But when you're a good musician, you can play those notes in any order you want, right? So same thing here. When you become really practiced at this, you can skip around the list. But for now, you're saying, hey, well, nothing else worked. Can I set you to be the downstairs? And sometimes it turns out that you can't, and you try it, and there's nothing wrong with that. Nothing wrong with trying an integration method and failing with it. So I've got, this is a 5.5 number 6, sorry, number 15. I'm doing the integral of 1 over 5 minus 3x dx. Is there an inside here? Probably not. I mean, you could really think of the numerator and the denominator as something that are inside, so that's fair thought, right? But it's not a super clear evidence of something inside. So we're going to go with the downstairs thought. And du is what? Negative 3 dx, right? Right? Yep. So I need a negative 3 upstairs, and I have to cancel it with a negative 1/3 outside. So I get minus 1/3 of the integral of 1 over u du. Right? Make sure you see that negative 3 dx is du. Right? So we get negative 1/3 times the ln of the absolute value of u plus c. And then u is what? 5 minus 3x? So I need the absolute value here. Right? 5 minus 3x could be negative, right? So I have to be careful about that. Let me give lines here. Where are you? 4 to 5. Yeah. So that's level 1, right? We know this is level 1. When I have 1 over u, I know that's the derivative of ln, right? So I'm just working it backward. So I guess when I'm testing these, I'm saying, well, let me just look at my original function, right? Y equals 1 divided by, what was it, 5 minus 3x? Yeah. So let me just look at my original function, and now let me put in my ddx of my answer, right? Of my answer, which I got, which ln of absolute value of 5 minus 3, minus 1/3, right? I don't need the plus c. It'll just confuse, it'll confuse everything. But negative 1 divided by 3. And it doesn't like something. What doesn't it like? It wants parenthesis here. There it is. And then look, on off, right? So put in the original function that I'm integrating as y, and then take the derivative of your integral, your antiderivative, and make sure they're matching. Nice. Still on level 6. Let's do, let's look at, come on. Let's look at number 18. These are fun to me. I think this is fun. I think the first derivative test stuff is a horror. But I'm ADD, right? So I don't want to do a problem for 3 pages. So, but these are fun. This is like a nice little puzzle, or at least try and make it fun. The integral of x squared over x cubed plus 1 dx. Is there an inside here? Well, probably inside of the square function, but that's just x. That doesn't really seem like it's going to work, but definitely there's a clear downstairs, so let's try that. U is x cubed plus 1. Du is 3x squared dx. So I need a 3. Yeah, I need a 3, and I need to cancel it with a 1/3. Everybody okay? So I have the 1/3 times the integral of what? What is the whole upstairs now? That's du. So I have, again, 1 over u du. So I get 1/3 times the ln of the absolute value of x cubed plus 1 all plus c. And of course I need the absolute value there because x cubed can be negative, right? Yes, because x cubed plus 1 has negative values, right? Yeah, when that thing inside it does never 0. So again, you can check it, right? Like the inside here is x cubed plus 1, right? So y equals x cubed plus 1. Does it ever go underneath the x-axis is the question, right? Does the red curve go underneath? Yes. So you need the absolute value. If that curve doesn't go under the x-axis, better yet, better not hit 0 either, right? Then I don't need the absolute value. Yep. Nice. Let's take a look at a problem that will try and trick you into thinking you take the downstairs, okay? So this is from our textbook. This is number 36. 34 and 36 have similar tricks to them. But again, there's no problem in you realizing it's not the right method. There's nothing wrong with that. You haven't done this long enough to know exactly what method you should use. So I'm giving them to you in order. So you kind of chip away at it. Eventually you'll see a square root thing and you'll know, oh, for sure it's got to be the inside, right? But not now. So be patient with it, okay? Let things happen. So we're looking at 34, 5.5 number 34. And I'm going to let it trick me, okay? I'm going, well, who sees an inside here? Who sees an inside? We all see a clear downstairs, but does anybody see an inside? What? Cosine is an inside of something squared. And that happens to be the right choice here. But let's see what happens if I pick u to be the downstairs. So u is 1 plus cos squared of x. What is du? 0 plus 2 times the cosine of x times another negative sine of x, right? dx. So du actually turns out to be negative sine 2x dx. And look at what I have. Do I have sine 2x? Can I get a 2 inside of the sine function? No, you cannot. Right? Sine x and sine 2x are different, right? Yes, you agree? They can't be equalized. Besides the fact that I can't get something inside this function. I can if it's an ln. That's why ln is those logs of functions are so special, right? That I can get something inside of it. This one I can't. I can't get something inside of this. Right? If I multiply by 2, does it go inside? No. A lot of you think it does, but it doesn't. So this one turned out to not work, right? So it turns out that u is cos of x. What's du? Nice, negative sine x dx, right? So I need a negative. I'm going to cancel it with another negative. So I now have the opposite of the integral of 1 plus u squared du. Ha! Look at it. What is it? What is it? What is the integral? Level 1. Yes, the negative inside became right. What is this integral, please? Come on. Nope. Arctan. Right? Arctan of u, which is cos of x. Our last 3 levels, level 10, 11, and 12, are inverse trig tricks, inverse trig methods. And the book likes to write c minus the arctan of cos of x. All right, here we go. Level 7. So level 7 is a u sub, but there's leftover variables. Okay, so this is a new level for us. Trying to think of why I'm thinking that I only have 10, maybe I only have 10 levels. Let me check my integral checklist from a previous semester real quick. Oh my God, it's so slow. Oh my God. It's painful how slow it is. How do I get back? You know, I guess I didn't put my, I have a integral checklist that I'm going to give you. I didn't post it here. Let me see if I can find it here. Please open. It says final exam solutions, but it's really just a checklist of the different types of integrals. Inverse trigs. Oh, I can't deal with it. Sorry. All right, let me get back to my problem. So here it is, level 7. It's gonna be a U sub, and you're gonna have a leftover variable. And so this could work. This method could work here, right? So let me just go to a brand new page here. So I've got the integral of x minus 2 times the square root of 5 minus x dx. Is there a clear inside? Hell yeah, that's inside, but this is really kind of feels like more inside, right? You agree with me there? So we're going to try u is 5 minus x, and then of course du is negative dx. So I need the negative, and I need to cancel it. When I put my u sub in now, right, I have du, right, but I got an x minus 2 times the square root of u du, right? So you can see the problem. The problem is here, right? Leftover x's. Could be a leftover x squared, it could be a leftover x cubed, etc., etc. Okay? So in this case, I want to try and change that x into some kind of u, right? So meaning if I solve this for x, what do I get? I get x equals 5 minus u. I now can put that in there. And then it turns out to be what? 3 minus u? And believe it or not, we're back to level 2, right? This is the opposite of 3u to the 1/2 minus u to the 3/2 du. Right? We agree with that? Yeah, good. So I'm just doing power rules now, right? This is, yeah, level, well, no, we're about to do level two. This is u to a half power. We know how to integrate that, right? So we have minus 3 u to the 1/2. We're going to add 1 to the power, divide by the new power. And we've got a plus u to the 3/2. We're going to add 1 to the power, divide by the new power, and add c. So 1/2 plus 1 is what? 3/2? And 3/2 plus 1 is 5/2. So I have minus 3 u to the 3/2 over 3/2 plus u to the 5/2 over 5/2 plus c. So it looks like, and I'm going to just change some order here. I get 2/5 u to the 5/2 minus 2. What's that again? I, well, it started with a 3, right? You okay with this 3? Yep, yep, yep. Say again? Okay. So I get 2u to the 3/2 all plus c. I would like to get an LCD, so I'm going to multiply by 5 over 5. Don't let me rush here. Make sure you're with me. So I see I can take out a 2/5, and I can take out a u to the 3/2. And of course, what do I have left over? I have u to the 2/2 minus 5. So 2/5 u to the 3/2, and then u to the 1, right? But u was what? 5 minus x, right? So it just becomes the opposite of x, right? So they get pretty nasty, these ones, okay? Yep. Yep, hold on. Nine to 10, I put this guy first now, right? And I did keep, change, flip. What happened at where? Yes. We typically don't do a lot of factoring in integration. If I want you to factor your answer when you are doing an integral, I will tell you, right? I'll say something like, make sure your answer is completely factored, right? And double check with what rule. Double check your answer with what rule. What rule are we going to use to double check our answer? Yes, can somebody answer me, please? How am I going to check my answer? What rule am I going to use? What? Which what? What? What rule? I'm asking how can I check my answer? What rule can I use to check my answer? No, what calculus can I use to check my answer? I don't need a test. I need to take the derivative. And what rule am I going to use when I take this derivative? Product rule. Product rule, right? What's my first function in the product? Negative 2/5 x. What's the derivative? Good. Second function is 5 minus x to the 3/2. Derivative is 3/2 times 5 minus x to the 1/2 times a negative 1, right? So it looks like I get, what? Help me there. 3 3/5, right? 3/5 x times the square root of 5 minus x minus 2/5 times the 5 minus x to the 3/2, right? It looks like I can factor out a square root of 5 minus x over 5. Yes? What? Where? Oh. Well, they both have a 5 downstairs, right? Yeah. So what's left over from my first piece? 3x. And what's left over from my second piece? What's left over from my second piece? 2 times 5 minus x, right? Yes? So I get square root of 5 minus x over 5 times 3x minus 10 plus 2x. Square root of 5 minus x over 5. It looks like I get a 5x minus 10. Oh, I can take out a 5 there, right? So I get square root of 5 minus x times x minus 2. What do you know? That's what I started with, right? That's the original problem. That was the original argument of my antiderivative, right? Right here. Nice. We only have a few more methods left. We should finish them tomorrow. There's a couple of really nasty ones. You should be working on things. You could almost do all of my old exams. You got to wait till tomorrow before you can do them all, okay? So, but you should be working on things, right? What's our quiz on tomorrow? Chapter 4.3, second derivative test. And I'm going to give you an optimization problem, right? So make sure you're doing those tonight so you can ask me about them in the morning. I mean, when class starts. Of course, you could send it to me before class. That's even better. Or the night before, tonight, right? All right.